Let's see another BST problem from LeetCode. It's a validate binary search tree. Let's try to understand this problem. So we need to validate whether this is a binary search tree or not. So you know the property of binary search tree. Every item in the left side should be lower than its parent. So this is and the right side should be greater than the parent. So this is the valid. So this is the valid BST. That's true. And this is not the valid case, and we need to analyze this clearly here. Yeah, and this is the problem here. I also spent good amount of time to do all the iteration and check whether it's valid or not, or anybody can also do the normal traversal, but normal traversal of the left right, the searching doesn't work. Why I'm saying, let's try to understand this problem, why this is not valid. Like if you see the left side, this is the lower number, this is the from the 5. In the right side, this is the bigger number. If you see, this is lower number and this is the bigger number. So why it is not BST, why this is not the valid binary search tree? Because we say like every item from this node in the left side should be lower and the right side should be greater, right? So that's good. So right side here it's greater, but this three item is not greater than 5. This satisfy for this node, but if it take a look for this, this should not be lower. So the first rule is every item in a right side of the node should be greater. So it should be greater than this 5. And the left side of 4 is also the 4 is also not so here it fails here itself. But I was talking about the situation, that's a different scenario that I struggle a lot here. Like let's say if this is a 7, if it is a 7, and this in this case also this is a this is invalid. This is not the valid BST. So why it is invalid? Because if you see, if you check, even if you put the 7, okay, 7 is greater, so good. And this side, like let's say we put the 9 is greater, but somehow like 7 and 9, so that's satisfied. And if you put the 3 here, it is less than this node, like a 7, then, but it is still it's not greater than this 5 node. So that's why that will not be valid, and that is the scenario here. Our normal traversal doesn't work. So we need to find out the different way. So one of the easiest way is we can traverse this thing with the inorder traversal, and when we traverse with the inorder traversal, then this number will be always in ascending number. And we can check if it is not in ascending number, then this is not a valid binary search tree. Like if I traverse in order, so in order from here we come to the left, and then there is nothing here in the left side, nothing, right side nothing, then in order in the middle, this one is, we print this. For if you see the entire tree, this is the middle, so 2, so 1 2. And then at the end we come here, there's nothing in the left right, we'll print the 3, so 1 2 3. So 1 2 3 is in ascending order. So this is the valid BST. If it is not ascending, then it cannot be the valid BST. And this is true for here also. If it is a 7, it's a 8, and if you put the 3, this all the number won't be in a descending order. So this won't be the valid BST. But in this case, if you maintain that whole list of this ascending number, it's going to take n space. So that's the one problem. But we can manage if you can maintain the previous value. and then previous value, and then we can just check, the current number whatever we get is greater than previous. If it is greater than previous, that's fine, otherwise return the false. So in that way we can minimize that space also. That is the one algorithm, but there is also another good algorithm, but for that we need to remember a few things, and if you do that, that also works. So in a second algorithm, we'll see the both algorithm one by one, but in a second algorithm, what I do for this node, I'll just put the left and the right limit, left and right. So left limit, I'll introduce two new variables, left and the right, and left I'll put lowest number there, maybe lowest int, and right number I'll put the highest int here, and then I will check. I'll check 2 is 2 should be always the less than the right, and 2 is always greater than left, and if that is not the condition, it's not a valid binary search tree, and 2 satisfies this, so that's a valid binary search tree, because 2 is less than, that's the right number, and the right value is the higher, bigger number, and that's less than. Okay, that's good. And in that case, we can move left and the right, both direction, and we can check all the value. But one thing we remember, when we move to the left, we do not change this left lower value, but we change the right bigger value, and the right bigger value will be this 2 when you move to the left. In the similar way, when we move to the right, then right value won't be changed, but the left value, that was the smallest number, the tiny number, that the smallest number, that will replace with this node. So, and we'll do for each node, and so only the one rule will put the introduce the two new variables, and we'll put the minimum number, and another variable very high number, and then another one is, we'll keep checking every step, we'll keep check. Okay, 2 is less than right, and 2 is greater than left. Okay, that's good. If not good, return false. Move this side, but when you move the left side, do not change left value, but change the right value with this. And move to the right side, do not change the right value, but change with this left value with this. So let's check this condition, it's a valid or not. If I move to the left side, then right value will be 2, and I will check the 2 is less, the 1 is less than 2, that's satisfies. And then we also check 1 is greater than the left was very minimum, and just 1 is greater. Okay, that's satisfy. When I move to the right, my left value will be 2, and the right will not change. It will check. Okay, 3 is less than right, good, and 3 is greater than left, and the left value is 2, greater than 2. Okay, that's good. So this is the valid scenario here. Okay, so let's see these two techniques here. So we'll do one by one. So first of all, I'm going to use the algorithm 1. Inorder traversal. Okay, for that, let me create another function, like is another helper function. Just I'm going to put here, just put that is valid. I'll pass the root. It's going to return the boolean. So in this case, I need to maintain the previous value, so I have to check the previous value. I have to check the previous value is, or the current value is greater than previous value. So let's create one variable like previous. I put 0 here, so the value can be also 0. So let me put the one more variable, just assign. And why I'm putting this assign here, because first time, I want this previous value to be assigned with 2, and once it assigned 2, then the assigned I'll make it true. So first I'll make the assigned false, and in that way I know that okay, there is a some value already, there is a previous value already assigned. We already have the previous value. I want to make sure. So once I have the previous value, then only I can check with the next value. So yeah, so I said like I wanted to assign this with a 2, not with a 2, but in order traversal, the first number will be 1. So I want to assign this previous value 1. So first time the previous value is 1. So once we have the previous value assigned, then when we move to the next node, we'll check whether the next value is the greater than previous or not. If it is not greater than, then return false. So that's why just I use this. I'm just going to pass the pointer for this previous and assigned. So I need to pass that in a caller, but here same time I want to pass the pointer. So this is the boolean. Okay, let me call this function here, age return age valid. This is root and then previous and address of assign. Okay, I will come here and I'll check if root is nil. If root is nil, then itself that's a valid. So I'm just going to return true. So in this case, if this is nil, then that's a valid binary search tree. So that's why I return true here. And then now first we'll start with this, and this is the in order traversal. Then I need to call, if it is not nil, then I need to call the left. I want to go to the left, so let's call this. Let's say the left is equal to this function is valid, and then root, whatever is the previous, whatever is assigned. So I call this left. I'll just take this for example. So it will goes here 1, and then after that again it will call the left. So the left, and the left side it will find the nil. So root nil. So come to this place is valid, and from here go to the left call. Again there will be the left call, and the left call will be root nil. Then it will return true. It will return true. Okay, that's fine. It's return true. So left will be the true in this case, first case, because that will be the nil on the left side. So I'm okay with this for now, left nil. And then once we reach here, I want to assign this 1 to the previous value. So this is nil, and it comes to, eventually it comes here, left is nil, then it comes here, return, and then I want to assign that. So if I say assigned is equal to true, and put the previous value. So start previous value is equal to whatever this root dot, because in that time comes to the left, return true, left will be true, but will still will be in this node, so we can use the root dot val. So we put that in a previous and assign is true. Okay, so first time. But before this, we can check we can check the conditions, like we can check the condition if assigned, if the assigned, that is assigned, is true, if assigned, and if it is assigned, then if it is already assigned, so first time it's assigned here, and then again we'll call this right. So just come here and then we'll check that this is the right. If you call the left, then root dot left we need to put, and root dot right here. So we'll go to the right again. So if you go to the right again, we'll start from here. So eventually, you know, for the right calling, eventually it comes to this place. Like let's say for this one we call, and then so one call for the left, that happened, and we already put it here. Come to this two place, and it will go here and then call the right. So in this case you can check here this conditions. Here you can check, like if assigned, if it is assigned, like previous value is assigned, this value is already assigned, and then we can check like let's come to this place again, and then we can check if this 2, so 2, this 2 is it's a root, so root dot val, if the root dot val is left, it should be the greater, because 1 and then next value is be 2 and 3, but root value is greater than previous value, then you can return false, and then the end you can return your left and right. So that's all algorithm 1. Let's run this and check for any error. So in prom, oh no, that's fine, because the previous value it is there, cannot use the previous value of the type, it is an int value. So here this would be the star. Two. So in that case we need to change if everything is 2. So in the binary search tree, you know, the each node should be the unique. If it is the same also, we want to return false. So that's why you need to check the less than equal to. Okay, let's try to understand once again with this problem. So the first time, you know, we'll call this 2. So we'll call is valid here with the 2, root not nil. Okay, we'll go to the left side, so it will call this will call left, and the still remaining is right, like it's call the left and then do the something and call the right. So it goes to the left portion, so again it will call the left, and when the second time from the 1 we call the left, then that already returned true, so it comes here, and the return it will true, so that's fine, left is true, and the value is not assigned, so it will do the other job. It will call assign the value, previous value there will be 1 root value, so 1 will be assigned a previous, and this is already assigned. It will not go to this place again, and it calls the right value. So for the right, from here it will call the right, so right will right will return the true, what, call the right will be true and true. let's try run it once again. So from call the 2, and from the 2 we are calling the left goes to the 1 and 1, and the remaining portion is still remaining for this 2, and it's for this 1 we call the left. And okay, rooted nil, so okay, let's call the left. So left portion, and that returns true. So this will be the true because that is the nil, and we're saying okay, root is nil, return true. So this one come to this place, it will not go here, and it will assign the previous value, assign true, and then it will go to the right, it will call the right. Okay, that's fine, it will call the right, and then right will return true. So for this it will return true. So for the 1, that's fine, for the 1 is everything, it returned true. Okay, so when we call the 2, so the left side it returns true for the left side, so it's the left side true, it's returned. And then again we'll go to the right side. For the right side, and before going to the right side, there is the left condition already returned true, and we want to go to the right side. Before that there is a pending conditions here, and we'll check value is already assigned. So yes, of course, 1 is already assigned in a previous, and we'll check root.val, that is 2 is less than the previous. No, 2 is not less than the previous 1, so it will not go to this place. Again we'll assign the previous value with the 2 here, and then we'll call the right value, right, so that is for the 3, and the 3 on the 3 it will call the left, that's a true, right also it's a true, and at the end left and right true. So that's a good. So I think we dry run is good here. Let's try for the algorithm 2. So let me comment this, or not here, but algo 1. Try another algorithm. So another algorithm, we can put some left and right. So I can say the left is, I can maintain some math min int, and the right I can maintain math at max int. Again I can call the auxiliary function another. I'm going to create another is valid here. Func is valid, root start tree node. Then we're going to pass left and right, so that's the int star. You can say left star int, right star int. Okay, it's going to return the boolean. So, and this is the is valid 2 function. So let's call this function return is valid 2, and you can pass root and then left and right. And here we can check if root is nil, then return true. That's good, that's a condition. Another condition we're checking, we maintain left and right here. So maintain the left and right, so we need to check this value less than right and greater than left. So you can check if root.val less than right. So right is right, let's make it the node itself, so left, and the type should be this one. maximum. I think that's good. That's fine. Root val, just checking with the root val. So root val is less than star right, and also root dot val greater than left. So this is the good condition, but this is a good condition we want to proceed. But if it is not the case, we want to return false. So I'll put here not, and then return false. Return false. But if it is a good, if it is a less, then we can move left and right. So that's why go to the left and right. So for the left and right, I can just call this function again, is value 2 with root dot left, and this time when we move the left, no change with the left, so left will be good, and we can change the right. So like right value, so right value is root dot val. In the similar way, I can call this again for the right. And for the right, the right value won't be changed, so I'll just put right. So I'm not going to change the right value, that's the initial logic, but left value will change, and that will be root dot val. So that's the logic here. So if anyone, any call left direction or right direction, any call return false, otherwise to return true. That is the valid binary search tree. So let's run this. Is valid to root left. We want to pass, okay, that's a left. Oh no, that is okay. Yes, that's the pointer. So what was the error? Line 38, use root value variable type int as a start argument. Root val. Root dot left, that's moving to the left direction, that's moving to the right direction, and we're passing root. Okay, we pass the root. Okay, so this should be so we do not need to maintain this pointer here, because we are not going to maintain like the same value again and again. So that should be just normal. That's fine. Let's see the Java solutions also for this. So Java solution algorithm 1. So let's change. This is the algorithm 2, I say, and this is the algorithm 1, I say. So let's see the algorithm 1 first. So first of all, we check the root. Like that's for the inorder traversal. So for the inorder traversal, root null, return true, or recall is valid 2. Okay, let me make it same. Maybe yeah, just invalid 2 here. So in this case, this is just understand this is a in order traversal, and we are checking the same thing. If it's already assigned, and if it is less than equal to root value, less than equal to previous value, return false. Yeah, so that's the same thing here also. And for the algorithm 2, or we check root equal now return true or is valid. We want to check the, we want to pass this root, and we want to maintain 2 values. So one is very minimum and one is very high value, and that's I passed here, and that is under this is valid function, and we're checking this condition. And we can quickly dry run, and we can check here also, like let's say, yeah, so we already dry run this with this example, so I think we're good for that. So okay, that's all for now. Thank you.